Sorry, we're back after a brief interruption. I had to move rooms quickly. Okay, so let's pick up where we left off. So what we want to do now is we want to characterize the stability of the equilibrium point xe equals 0, right? We said that this is kind of this canonical choice of equilibrium points. Okay? So how are we going to do this? Well, if you go ahead and you take a look at the basic definitions of Lyapunov stability, right? What you're trying to do is you're trying to characterize the difference between the trajectory of your system, x of t, and the equilibrium point xe, right? But for xe equals 0, what's kind of nice is x of t minus xe is just equal to norm x of t, right? Okay, so here's what we're going to do. We're going to examine the continuous time case in particular, kind of using this observation, all right? So how do you compute the norm of x of t for the continuous time case? How do we find a nice upper bound? Well, we know that this is equal to the norm of the product of the state transition matrix phi of t, t naught, multiplied by x naught, right? And if we're assuming that we're using the operator norm to induce a norm on the matrix phi, then this guy is less than or equal to norm phi of t, t naught, times norm x naught, okay? So then the basic idea is, if we can control the size of the norm of phi of t, t naught, then we can make stability claims, okay? And this is because all we're trying to do is control the norm of x of t, right? And we clearly see the norm of x of t is kind of upper bounded by this norm of phi times the norm of the initial condition, okay? So if we're able to control the norm of phi, then we should be able to figure out some sort of stability characteristic, okay? And it turns out this actually gives us a, kind of sharp characterization of stability, which essentially says, if the norm of my state transition matrix is bounded for all time, then I'm guaranteed to have Lyapunov stability. It turns out the converse of this is also true, okay? So let's go ahead and state a theorem concerning this state transition matrix characterization of stability. So here I'm just going to focus on the continuous time case. If you're interested in the discrete time case, you can find the details of that in the notes, okay? Let's go ahead and state this theorem. Okay, so theorem, which I'll call the state transition matrix characterization of stability. So I'll say let phi be the state transition matrix of an unforced continuous time linear time varying system. All right, so standard state transition matrix. Okay, so the equilibrium xe equals 0 is first stable in the sense of Lyapunov, or Lyapunov stable, and it's going to be Lyapunov stable if and only if, which I'll write as IFF, there exists a k greater than or equal to 0 such that phi of t comma 0 is less than or equal to k for all t and r greater than or equal to 0, okay? So note that here we're not bounding phi of t comma t naught. Turns out it's sufficient just to bound phi of t comma 0, all right? So this is true in the continuous time case. In the discrete time case, we need to bound t, t naught, but continuous time is a little bit nicer, okay? All right, so second, we have a characterization of global asymptotic stability in terms of the state transition matrix. It says that the equilibrium xe equals 0 is globally asymptotically stable if and only if the limit as t goes to infinity of phi of t comma 0 equals 0, okay? All right, fantastic. So how are we going to prove this? Well, first we're going to make a couple of simplifying assumptions that actually don't lose us any generality, all right? So we'll say without loss of generality, we will assume the norm on phi is the induced operator norm, okay? So this is the norm induced by the norm on Rn, all right? And the reasoning for this is that the operator norm comes with a lot of really nice properties, right? For instance, like this submultiplicative property and all sorts of nice interactions with these standard vectors in Rn. Okay. So due to norm equivalence, it actually doesn't matter, which norm we pick, because all we're interested in is some boundedness and convergence properties. Okay? All right, fantastic. So with that said, let's start by proving the forward direction of 1. Okay? So I'll say, suppose there exists a constant k greater than or equal to 0, such that norm phi of t comma 0 is less than or equal to k for all t in R greater than or equal to 0. Now what I want to do to kind of prove Lyapunov stability is to get this epsilon delta argument in terms of the norm of x of t, right? Or the norm of phi of t, t naught, x naught. Okay, let's go ahead and try to do this. So what I'll say is, first, let's go ahead and fix an epsilon greater than 0. Okay? Now remember, what we want to do is we want to find a delta greater than 0 such that we're able to stay within this norm epsilon radius of our initial condition, of our equilibrium point for all time. All right? So I'll fix an epsilon greater than 0, and I'll also fix an initial time t naught. Actually, that doesn't need to be greater than or equal to 0. So I'll fix a time t naught in R. Okay? So what I'm going to do next is I'm going to try to control the norm of phi of t, t naught, x naught. All right? And we know that this is simply equal to the norm of phi of t, t naught, x naught, right? That's just by definition of the solution to a linear time-varying system. Now let's go ahead and bound this thing above, all right? Now how do we come up with a bound on this phi of t, t naught, x naught? Well, we know that we have a bound on phi of t comma 0, right? So in order to actually apply this bound, we need to split up this phi over here into 2 different pieces, okay? So using the composition property of the state transition matrix, this is equal to phi of t comma 0, phi of 0 t naught, right, multiplied by x naught. Now let's go ahead and use the property of the operator norm to split this norm up into 3 pieces. All right, so this in turn is less than or equal to the norm of phi of t comma 0 multiplied by the norm of phi of 0 t naught times the norm of x naught. Okay, now we can go ahead and apply our bound, right? Because we recognize, okay, that's the quantity that we know how to bound, all right? So we go ahead and apply this. What we could do is this is equal to k times norm phi of t, 0 t naught multiplied by norm x naught, okay? What we wanted was to make this less than epsilon for all time, all right? So clearly what we could do is we can pick the norm of x naught to be less than epsilon over norm k, k times norm phi of 0 t naught, and then that'll give us the desired inequality. Okay, so we conclude that there exists a delta, which is determined by this quantity, that gives us this Lyapunov stability property. Okay, so that's the first direction, right? Now what about the second direction? So what do we have now? Well, here's what we have. Let's say, suppose xe equals 0 is stable in the sense of Lyapunov. Now remember, the definition of stability in the sense of Lyapunov is a little bit unwieldy, right? So I'll just kind of write it out, and you'll kind of see what I have, all right? So for a fixed time t naught in R, what we have is for all epsilon greater than 0, or I'll just say for a fixed epsilon greater than 0, there exists a delta, right, which potentially depends on t naught and depends on epsilon. This is greater than 0, such that the norm of x naught being less than delta of t naught comma epsilon implies that the norm of phi of t, t naught, x naught will be less than epsilon for all t greater than or equal to t naught. Okay, so here I'm just using this delta of t naught epsilon to just emphasize the fact that this depends on t naught and epsilon. Okay, fantastic. So what are we going to do now? Well, what we'd like is to find a bound on the norm of phi, right? The bound on the norm of our state transition matrix, where the second argument is just time t equals 0. Okay, so I'll just say take your initial time t naught equals 0, right? And let's go ahead and fix some epsilon greater than 0. Okay, then what do we have? X naught being less than delta of 0 comma epsilon will imply the following. Well, it implies by definition of stability phi of t comma 0 comma x naught is less than epsilon, right? Now let's go ahead and rewrite this in terms of our state transition matrix. So this implies phi of t comma 0 multiplied by x naught is less than epsilon for all t, for all t greater than or equal to 0. Now what I'm basically going to do is I'm going to rework this left-hand side such that it kind of looks like the definition of the operator norm, okay? So what I can do is, assuming x naught is non-zero, right, I can go ahead and rewrite this left-hand side as x naught multiplied by phi of t comma 0, x naught over norm of x naught, all right, less than epsilon. Okay, so now what we have inside here is we have phi multiplied by a unit vector, okay? So if I go ahead and I take the supremum over all x naught, satisfying delta or norm of x naught less than delta of 0 epsilon, what I'll actually find is that this guy inside here gives me the definition of the operator norm of phi, okay? So what I do is I take the supremum over norm x naught less than delta of 0 epsilon, x naught non-zero, x naught times phi of t comma 0, x naught over norm x naught less than epsilon. Now this first term over here is clearly maximized by taking x naught approaching delta of 0 epsilon, so we can just replace that directly by delta of 0 epsilon. And then the second term over here, if we want to maximize the product of a matrix and a unit vector, that's the definition of the operator norm, right? Okay, so what we kind of end up with is this is equal to delta of 0 epsilon times phi of t0. And in taking the supremum, instead of getting a strict less than, this gets relaxed to a less than or equal to, okay? So what we find is phi of t comma 0 will be less than or equal to epsilon over delta of 0 comma epsilon, all right? And that's our upper bound, which holds for all t greater than or equal to 0. Okay, so the result then follows. Nice. Okay, so that proves kind of this first point that we wanted to prove, right? Stability in the sense of Lyapunov is one-to-one with this state transition matrix being bounded for all time, right? Now we want to prove part 2, which says it's globally asymptotically stable if and only if the norm of the state transition matrix limits to 0, okay? So let's go ahead and prove part 2. Okay, so part 1 done. Part 2, all right. So first what we'll say is, suppose the limit as t goes to infinity of the norm of phi of t comma 0 equals 0, right? Now what we want to show is that the equilibrium point xe equals 0 is globally asymptotically stable, okay? So remember, there's two things that we need to check. First, we need to check stability in the sense of Lyapunov, right? And second, what we need to check is this convergence property, okay? So for stability in the sense of Lyapunov, since phi of t comma 0 is continuous, and the limit as t goes to infinity, norm of phi of t comma 0 equals 0, what we actually have is that norm phi of t comma 0 is bounded, okay, for all t greater than or equal to 0. Okay, so there exists some constant k that upper bounds this because it's continuous and because it limits to 0. All right, so by part 1, we get x equals 0 is stable in the sense of Lyapunov. Okay, great. So that's stability in the sense of Lyapunov. Now we want to check the limiting property. All right, so I'll say fix a time t naught and r, fix an initial condition x naught and rn, right? Since we're going for global asymptotic stability, we want arbitrary initial time and arbitrary initial state. Okay, so then what we have is that phi of t naught x naught, which equals the solution of our system, is, by a similar process to the above, less than or equal to phi of t comma 0 multiplied by phi of 0 comma t times x naught. All right. Now, if we posit the limit, then essentially this quantity is upper bounded and lower bounded by 0. Okay. We get 0 less than or equal to lim t goes to infinity, phi of t, t naught, x naught, which is less than or equal to 0, right? Because if we posit the limit on this side, this guy decays to 0, right? Okay. So then we conclude the limit property. Okay, fantastic. So that's the forward direction, right? Now what about the reverse direction? So in the reverse direction, what we want to show is under the assumption of global asymptotic stability, we're guaranteed that the limit of the norm of the state transition matrix equals 0. Okay? So let's say now assume xe equals 0 is globally asymptotically stable. All right? So what does this imply? Well, this implies for all x naught in Rn, we have the limit as t goes to infinity of phi of t. I'll just take times 0. Okay? Phi of t comma 0 times x naught equals 0. Okay? All right. Well, what else do we have? Well, now by being a little bit clever with our choice of initial condition, we can actually show that phi itself will converge to 0. All right? So I'll say take your initial condition x naught equals ej in Rn, right? So this is the jth standard basis vector in Rn, which contains a 1 in component j and zeros everywhere else. What the above tells us is that the limit as t goes to infinity, norm of phi t0 ej equals 0, right? But what is phi of t comma 0 times ej? Well, that's the jth column of phi of t comma 0, okay? So this tells us column j of phi t comma 0 converges to 0. And since this is true for all j, what we conclude is that phi of t comma 0 goes to 0 as t goes to infinity. All right? And what we then conclude is that the limit as t goes to infinity of norm of phi of t0 approaches 0 as t goes to infinity. Okay? So essentially the argument that we've made is if we're globally asymptotically stable, then by picking initial conditions that are, ej vectors, right, the standard basis vectors, we prove that each column of our state transition matrix goes to 0. Then that implies the entire state transition matrix goes to 0. Then that implies its norm goes to 0. All right? And that's a proof. Okay, so let's summarize what we've just done. What we've just said is that the stability of the 0 equilibrium point, right, xe equals 0, has a sharp characterizations via limiting and boundedness properties of the state transition matrix, right? So this is really nice, right? We have if and only if conditions, which are kind of the ideal conditions to have, right? A perfect characterization. But this only holds for xe equals 0, right? And what about other equilibrium points? Well, let's take a look, right? So our next question is, what about other non-zero equilibrium points, right? So that's our first question. And our second question is, above we only characterize global asymptotic stability, right? So my second question is, what about local asymptotic stability, right? Maybe we can get away with some weaker conditions. So it turns out the answer to these two questions is really interesting for linear systems, okay? So what we find out is that 0 is the only possible asymptotically stable equilibrium point, and further, an equilibrium point is locally asymptotically stable if and only if it's globally asymptotically stable, okay? So this is certainly not true for a general nonlinear system, but for linear systems, this turns out to be the case, okay? It's a really nice property. Okay, so let me go ahead and state this as a proposition. We'll go ahead and prove it. So, proposition, which we'll call local asymptotic stability and non-zero equilibria. Okay. We'll say consider an unforced continuous time linear time varying system. Then what do we have? Well, first we have local is equivalent to global, right? So an equilibrium point xe equals 0 is globally asymptotically stable if and only if it is locally asymptotically stable, okay? So that's the first point. Now the second point is xe equals 0 is the unique asymptotically stable equilibrium, okay? So xe equals 0 is the unique asymptotically stable equilibrium point, okay? So if I give you any point and I say this equilibrium point is asymptotically stable, then guaranteed it has to be xe equals 0, okay? There's no other point out there. All right, so let's take a shot at proving these two. So first, let's go ahead and do this local to global proof, all right? Let's start with proof 1. Well, fortunately, one direction of this is really easy, right? Global asymptotic stability should imply local asymptotic stability, okay? Implies local asymptotic stability, check, all right? That one's not too hard. Now, what about the other direction? Well, so that was the forward direction. Now let's try the reverse direction. There's a couple different ways we can go about proving this other direction, but I'll just show you one way that uses this property that we previously showed above, okay? So there's other, maybe more direct ways, but I just want to show you how you can use the previous result. All right, so if we have local asymptotic stability, what do we get? Well, what we get is there exists some constant such that if we stay within the region defined by that constant, we'll limit to our equilibrium point, right? So I'll say, suppose due to local asymptotic stability, there exists some constant m such that norm x naught less than m implies that the limit as t goes to infinity of phi of t comma 0 x naught equals 0, okay? So this m is particular to t naught equals 0. Okay, well, what do we have? Well, now we can get a little bit clever about our choice of x naught once again, right? So we showed earlier that, by picking x naught equals these standard unit vectors, we can show that our entire state transition matrix converges to 0, right? What are we going to do in this case? Well, now, because of this local bound, right, we're not guaranteed that our standard basis vectors will be of the correct norm, all right? So what I'll do is I'll just kind of adjust their size a little bit, right? So I'll say, let Vj equal Ej, jth standard basis vector, over m plus epsilon, where epsilon is some arbitrarily small number, okay? So what I'm doing is I'm taking the jth standard basis vector and I'm kind of just squishing it down until it fits in this region of initial conditions, all right? Well, what we have from the above is that the limit as t goes to infinity of phi of t comma 0 times Vj is equal to 0, right? Because we're within this correct ball of initial conditions. But since Vj is just a scaled version of the Ej vector, this still implies column j of phi of t comma 0 needs to converge to 0, right? Because we're just picking out a scaled version of column j. Now this then implies that by similar reasoning to above, the norm of phi of t comma 0 goes to 0, and then by the previous theorem, this implies global asymptotic stability. Okay? So that proves the reverse direction. So we've just shown that global asymptotic stability and local asymptotic stability of x equals 0 are in fact equivalent for a linear system. Okay. Now let's move on to point 2, and I'll just give you a quick sketch of point 2. Okay? So what we'll say now is, suppose there exists an equilibrium point, xe equals Rn, that is globally asymptotically stable. All right. Since in point 1 we showed global and local are the same thing for linear systems, it's just sufficient to prove this guy for global asymptotic stability. Okay. All right. So here's what we're going to do. What we're going to do is we're going to effectively show by a couple of steps that xe, even though we've assumed it to be arbitrary here, must be the 0 equilibrium point in order to have this property. Okay. So my first step in doing this is I'm going to perform a change of coordinates, all right? So I'm going to define z equals x minus xe, all right, which effectively just shifts shifts this equilibrium point to be at the origin of some new coordinate system, all right? So for z equals x minus xe, I then have z dot equals x dot, right? Which equals a of t times x. And then this in turn is equal to a of t times z plus xe, right? But a of t times xe is equal to 0 for almost all t, okay? So for almost all t, this guy is equal to a of t times z, all right? So here's what we have. If z equals x minus xe is globally asymptotically stable, then what do we get? Well, since we have z of t equals phi of t 0 times z at time 0, right? This implies that if z equals 0 is globally asymptotically stable, then the limit as t goes to infinity, norm of phi of t comma 0 equals 0, right? But what else does this imply? Since this state transition matrix is going to be the same as the one for the original system, right, because A is the same, this implies xe equals 0, or excuse me, this just implies 0 is globally asymptotically stable for x dot equals a of tx, right? So now what we have is both xe and Rn and 0 are globally asymptotically stable. And since we have two globally asymptotically stable equilibrium points for the same system, what this implies is that they need to be the same equilibrium point, right? So this implies xe equals 0. Okay? So what we've just shown is that if we take another globally asymptotically stable equilibrium point, we require that that equilibrium point is the 0 equilibrium. Okay, fantastic. Okay, fantastic. So what we've just done is we've done, I don't know, like a fairly complete study of stability of linear time-varying systems in continuous time, right? We kind of showed that the 0 equilibrium point is the one that exhibits the most interesting behavior, right? We came up with a sharp characterization of its stability, and we showed that any non-zero equilibrium point can at best be stable in the sense of Lyapunov, right? It's not going to be asymptotically stable. Okay, so usually what we do at this point, right, is after we've kind of said some interesting things about the time-varying case, we specialize to the time-invariant case, right? That's exactly what we're about to do. All right. So let's go ahead and talk about our third and final point for today, which is the stability of linear time-varying systems. Okay. Oh, excuse me, linear time-invariant systems. My goodness. I'm not going to repeat myself too much. Okay, so let's kind of sketch out what we might be able to do in this linear time-invariant case. Now, remember, there's usually a couple of different things that we find, right? We find that there's a lot more structure present in this linear time-invariant case, and we could use that structure to come to stronger conclusions about the behavior of our system, okay? So above, what we had said is we can do all these nice different characterizations of our system in terms of the state transition map, right? But what we remember is that in the time-invariant case, state transition maps have a super nice and simple form, right? Phi of t comma t naught equals exp of a, t minus t naught, where this is the matrix exponential. So this is for a continuous time LTI, right? And then in discrete time, we have phi of k comma k naught is equal to the matrix power a to the k minus k naught. Okay, so this is for discrete time LTI. Okay, so what are some consequences of this? Well, if we see an exponential and we see a matrix power, right, maybe we could be a little bit more specific about what modes of convergence we're going to have, right? Maybe we can do better than just having a blanket asymptotic stability. Okay, maybe we can get an actual specific convergence mode. And this is exactly what we're going to do now, okay? So if we see an exponential and we see a matrix power, maybe we can get exponential convergence, right? Maybe we can get, I don't know, geometric convergence if we have this power, okay? So what we're going to do now is we're going to set out a definition for exponential stability, all right? So definition, exponential stability. Now, once again, I'm going to state this definition for a general system, right? It doesn't have to be linear time invariant or, discrete time or continuous time system. It's just going to be some arbitrary dynamical system, right? Okay, so I'll say consider an unforced dynamical system with state transition map phi, right? Unforced state transition map phi, state space sigma equals Rn, and equilibrium points xe in Rn. Okay? So first what I'm going to do is I'm going to talk about continuous time exponential stability. So continuous time local exponential stability. All right? So if we have a continuous time system where t equals r, then xe is locally exponentially stable, or LES, if for all time t naught in r, what do we have? Well, we have that there exist constants, epsilon naught greater than 0, m greater than or equal to 0, and finally alpha strictly greater than 0, such that the following hold. We have x naught minus x equilibrium less than epsilon naught, right, which looks like a locality condition, implies that phi of t, t naught, x naught, minus your equilibrium point xe is going to be less than or equal to m e to the minus alpha t minus t naught multiplied by the norm of your initial condition. So x naught minus xe, and this should hold for all t greater than or equal to t naught. Okay? So essentially what we're saying is if we start sufficiently close to our equilibrium point, we should be able to get an exponential decay bound to our equilibrium point. All right? And here it's really important to point out we're not just asking that we get exponential convergence, but we're asking that this exponential convergence have a particular structure with respect to the initial condition, right? It's a decaying exponential multiplied by the norm of our difference, right? The norm of our initial difference, okay? So it's not like we have some arbitrary function of this over here, right? That wouldn't be exponential stability. We just have direct multiplication by this norm. Okay, fantastic. So that's continuous time local exponential stability. What about discrete time? Well, in discrete time, instead of having an exponential term, we'll have a geometric decay term, okay? So this is kind of what we saw before in this Laplace Z transform case where we take an exponential and we convert it to a geometric term. It's going to be the same thing here, okay? So discrete time, local exponential stability. So if t equals z, then xe is locally exponentially stable if for all k naught in z, there exist constants epsilon naught greater than 0, m greater than or equal to 0, now alpha, which belongs to 0, comma 1, okay, where 0 is included and 1 is excluded, such that the following holds. So first we have locality, x naught minus xe less than epsilon naught. This implies phi of k, k naught, x naught minus x equilibrium is less than or equal to m times alpha to the k minus k naught times your norm of x naught minus xe, okay? And this should hold for all k greater than or equal to k naught. Oops, k naught, there we go. Okay, so basically what we're asking for here is we're asking that we get a geometric decay, right? If you remember from before, the reason for this geometric decay is that if we take an exponential decay in continuous time, and then we sample that exponential decay at a fixed time interval, what results is a geometric decay. Okay, so this is really just a natural way to pull a geometric term out of an exponential term. Okay, so now we can go ahead and we can make these definitions global. All right, so I won't state the full definition because I'm sure you can imagine where I'm going with this. Right, so this is continuous time global exponential stability, and this is going to be the same as the continuous time local exponential stability, but without the epsilon naught condition. Okay, so if instead we just say that this bound over here holds for all initial conditions and for all initial times, then we have global exponential stability. Okay, so it's just kind of the same thing as local to global asymptotic stability, where we just delete this initial condition needs to be near xe. Okay, now for discrete time we have the same thing. All right, discrete time global exponential stability. This is same as discrete time local exponential stability, but also without this extra epsilon naught condition. Okay, fantastic. Okay, so what are we going to do now? Well, we've kind of laid out these nice definitions for local exponential stability and global exponential stability. What I'm going to spend the remainder of this lecture doing is giving you a sketch proof of how we can characterize continuous time local exponential stability, global exponential stability using the eigenvalues of the A matrix. Okay? So, again, I'm just going to briefly mention the discrete time case all the way at the end. Why am I jumping straight to the global case? Well, it turns out, as with asymptotic stability, local and global are equivalent, okay? So this is something you can prove, but since we already kind of discussed it for asymptotic, I'm not going to go through the analogous proof for exponential here. Okay. All right, so here's what we're going to do. So what we want to do now is we want to characterize the local exponential stability of, oops, oh my gosh, I keep saying local. So global exponential stability of x dot of t equals a times x of t, right? So this is the continuous time LTI case. And a nice property of LTI systems that we've kind of seen so far is that if a property holds at t naught, t naught equals 0, then it holds for any t naught, right? Because in a linear time invariant system, right, objective times don't matter, right? It's only the difference in time past that matters, okay? So this is effectively to say that if we're able to achieve exponential stability at time t naught, we'll be able to get it for any time, okay? So for that matter, I'm going to just assume we're taking our initial time t naught equals 0. Okay, so what do we want to do? Let's say I take an initial condition x of 0 equals x naught. Then if I want to examine the norm of the solution of this system, right, if I want to figure out the global exponential stability of the equilibrium point 0, then what do? I take the norm of the difference, x of t minus xe, right, which for xe equals 0 just equals norm x of t, right? This guy is equal to x of at times the initial condition at time 0, which is x naught. Then we can bound this above x of at times norm x naught. All right? So then from this very basic kind of bound, what we see is that if we can bound norm x of at less than or equal to me to the minus alpha t, then we'll get the conditions for global exponential stability, right? Because we already have this nice direct multiplication by x naught hanging out here. Okay, so our main goal is then to show that under certain conditions on our A matrix, we're able to get this decaying exponential bound on the norm of the matrix exponential. Okay, so what we want to do now is we want to find conditions where we get this bound. Okay. So how do we come up with a nice bound on the size of the matrix exponential? Well, for an arbitrary matrix, this is kind of hard to do, right? Because we don't really understand in closed form what an arbitrary matrix exponential will look like, okay? But what we do know how to do is we do know how to compute in closed form the exponential of a Jordan block, right? Or at the very least, we know how to do this in theory, right? In practice, like we had mentioned a little while ago, there are some numerical issues that arise with this. But in theory, this is a good thing to do, right? The basic idea is, let's start with a Jordan block. Okay? So what I'm going to do now is I'm going to try to compute an upper bound on the norm of exp of jt, where j equals lambda I plus n naught, right? Where remember n naught is the matrix which has zeros everywhere, but on the super diagonal, where it has a bunch of ones, okay? So just as a quick reminder, exp of jt is equal to e to the lambda t times 1s, t's, right? And this pattern kind of continues all the way until we get t to the n minus 1 over n minus 1 factorial, all the way up here, right? And then there's zeros everywhere else. Okay, so how are we going to find the size of this Jordan block? Well, there's a couple of different things that we could do, right? First, we notice that this block is filled with polynomials, right? So maybe we could find a bound on the norm of this Jordan block in terms of an exponential and a polynomial, all right? So that's the first thing that I'm going to do, all right? So I'll say proposition, which is the exponential polynomial Jordan bound. What I'll say is consider a Jordan block J equals lambda I plus n naught, where this belongs to Rn by n. Okay? Actually, let's take this in Cn by n. All right? So then there exist constants C naught, C1, all the way up until Cn minus 1, such that the norm of exp of jt is less than or equal to e to the real part of lambda times t multiplied by the polynomial c0 plus c1t plus cn minus 1 t to the n minus 1. Okay? And the proof of this is effectively just, let's go ahead and let's take a really goofy norm on our matrix exponential. Okay? So let's take the norm, matrix norm, which sums up absolute values of each entry. Okay? And what we'll find is that we effectively, in this norm, get exactly the result that we're looking for. Okay? Exp of jt is less than or equal to, first, the magnitude of e to the lambda t, which is just equal to the e to the real part of lambda times t, times the sum of magnitudes of all these different components, which for t greater than or equal to 0 will just be a polynomial, right? Times c0 plus c1t plus c to the n minus 1 t to the n minus 1. And this needs to hold for all t greater than or equal to 0. Okay? So that directly gives us a nice way to compute an upper bound on this. Now, due to norm equivalence, this inequality will in fact hold for some set of constants for any norm out there. Okay? Because norm equivalence just tells us we can scale up these norms and we'll be fine. All right? Okay, so let's do a very quick sketch proof of this. Okay, so now what we've done is we've shown that we could bound the norm of our exponential using the product of an exponent, right, a real exponent, and a polynomial, right? The definition of exponential stability doesn't have any mention of polynomials, right? So we want to get rid of this polynomial. So what we're going to do now is we're going to show that we can control the size of a polynomial with an exponential of any positive decay rate, okay? So this is exponential polynomial bound, all right? And what this says is consider a polynomial Pn of t equals an t to the n plus a1t plus a naught, right? Then for all epsilon greater than 0, there exists some constant m greater than 0 such that the magnitude of Pn of t is less than or equal to me to the epsilon t. This holds for all t greater than or equal to 0. Okay? So what this tells us is that we can actually bound above a polynomial with an exponential with an arbitrarily small positive rate. Okay, so the proof of this, I'm just going to go a little quickly here. If we actually compute out this exponential, e to the epsilon t, right? This is equal to 1 plus epsilon t plus dot 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 plus epsilon to the n, t to the n over n factorial, plus the rest of this infinite sum, right? From k equals n plus 1 up until infinity of epsilon to the k, t to the k over k factorial, right? So if I multiply it by m, what I'll get is that is m plus m times the rest of this, right? Now for t greater than or equal to 0, this guy is greater than or equal to 0, right? That's pretty clear. And same goes for this, right? So what I can basically do is I can just pick m large enough such that the coefficient of the t to the I term is greater than or equal to the magnitude of a to the I. Okay? So then what we'll effectively have is that this m e to the epsilon t, the first n terms will bound above the polynomial, and the rest of the series is positive. Okay? So that gives us our upper bound. All right, so that's a proof. Okay, so let me go ahead and directly state our stability theorem. Okay, so using these two tools above, where we have Jordan blocks become exponential and polynomial, and then we can bound above a polynomial with an arbitrary exponential with positive rate, we arrive at the following theorem. Okay, so we'll say consider an unforced continuous time LTI system x dot equals ax. All right. So the equilibrium xe equals 0 is globally exponentially stable if and only if, for all eigenvalues lambda of a, the real part of lambda is less than 0. Okay? So if the real parts of the eigenvalues are all less than 0, we're going to have global exponential stability, and the converse of this is true. Okay? So this is necessary and sufficient. Okay. So I just want to make a couple quick remarks. So the set of all constants lambda in C such that the real part of lambda is less than 0 is called the open left half plane of the complex numbers. Okay, so this condition is equivalently stated. All of the eigenvalues need to belong to the open left half plane. And this condition that real part of lambda is less than 0 for all eigenvalues of A is also said A is Hurwitz. Okay, so a Hurwitz matrix is one that satisfies this eigenvalue condition. Okay, so I just want to give you a quick proof sketch, and I'll just prove the case where A is a single Jordan block. Okay, so the general case is essentially proven by transforming A into its Jordan canonical form and bounding each Jordan block above, then bounding the norms of the transformations into Jordan canonical form. Okay, so it's not too much longer than what we have here. Okay, so I'll say we'll just take the case where A equals J equals lambda I plus n naught, right? Then I have that the norm exp of jt will be bounded above by e to the real part of lambda times t, right? And this will be multiplied by some polynomial, Pn of t, okay? So this is what we had said above, right? Now I'll apply this exponential polynomial bound. So I will say pick a value epsilon such that the real part of lambda plus epsilon is still less than 0, okay? Because here we're assuming the real parts of lambda are all less than 0, so we'll be able to get this value of epsilon, right? Now using this, we conclude the existence of a constant m such that the following inequality is satisfied. So exp jt will then be less than or equal to me to the real part of lambda plus epsilon times t, okay? Where now we've used this exponential bound on Pn of t, and we just kind of multiplied it in. And the consequence of this is that we get a decaying exponential bound on norm exp of jt, okay? Because this real part of lambda plus epsilon is still going to be less than 0, okay? So this gives us a proof where A equals lambda I plus n naught, and the real part of lambda is less than 0, okay? So based on our argument from earlier, this tells us that we get exponential stability, global exponential stability, okay? So the converse direction, you could prove it by contradiction. So you pick an eigenvector corresponding to an unstable eigenvalue, right, where the real part of lambda is going to be greater than or equal to 0, and then you show that you don't get exponential conversions when you take that as your initial condition. Okay? So again, the general case just follows by, computing bounds for each Jordan block and kind of taking the maximum of all of those. All right, so the details of this are in the notes if you're interested in taking a more in-depth look at that. Okay, so that gives us the conditions for global exponential stability for a linear time invariant system in continuous time. In discrete time, we get similar conditions, which just says we get global exponential stability if and only if the eigenvalues lambda satisfy magnitude of lambda is strictly less than 1. Okay? Because if you look at a to the k, then you get, if this is the scalar case at least, if a to the k, if a belongs to 0, 1, then you get convergence down to 0 geometrically. Okay? So think of scalar case. The proof of this follows very similarly to this exponential case above. Okay? So this discrete time condition where the eigenvalues lambda of a satisfy magnitude of lambda less than 1, this is called a Schur matrix. All right? So in continuous time, you get stability, global exponential stability, if and only if your matrix is Hurwitz. In discrete time, you get global exponential stability, if and only if your matrix is Schur. Okay? All right, we'll leave things off at there. Thanks for watching.